Welcome to the Power of ERDC podcast. I'm your host, Tim Reeves. In the vast Indian and Pacific Oceans regions, known as Indo-Pacific, a threat emerges from the Gobi Desert, massive dust storms capable of jeopardizing critical military operations. For years, forecasters have often overlooked the role of seasonal snowpack and frozen soil, conditions that can dramatically increase a dust storm's hazardous area. Now, a study by ERDC's Weather Effects Team has quantified the effects of these dust storm conditions, translating the data and turning into actual information for military planners in the region. With this study, commanders have additional information they need to safeguard vital flight, ground, and surveillance operations. Join us to discuss this work and the Weather Effects Team is Dr. Ted Letcher, a research physical scientist at ERDC's Cold Regions Research and Engineering Laboratory. Morning, sir. How are you?
I'm good. How are you?
I'm good. I understand as we do this, there are several inches of snow where you are, and I'm glad that I am not near those several inches of snow. So we'll start at like the 50,000 foot level for this conversation and know that we're going to get back to the main challenge of the dust storms and modeling and such. But for a quick background, tell me about the ERDC Weather Effects Team, the main research mission, and some of the expertise you and your team bring to the table.
Sure. Yeah. So the ERDC Weather Effects Team is, what I would call sort of a growing interdisciplinary group within ERDC that's focused broadly on research and development of new Army decision support capabilities that, kind of has a common theme that they all try to incorporate in some way weather data. Some of our goals include strengthening warfighter geo-enabled decision support with applications for applied engineering functions, tactical and strategic planning, and then other, just kind of general terrain management applications. But like I said, our key through line is that we aim to achieve these goals by incorporating weather data and oftentimes in new and I would say novel ways. So the team is pretty interdisciplinary. I think that's probably the biggest strength of this group and one of the things that makes it unique. We include experts from across all of the ERDC labs, not just meteorologists, but also experts in geomorphology, remote sensing, machine learning, hydrology, and engineering. And I'm sure that doesn't encompass everybody in our group either. My opinion on this is that's kind of the diversity of that expertise is really what enables the group to tackle these large and really complicated research and data analysis problems.
So
that's us in a nutshell.
Well, so not to interrupt you, and I apologize. So, you talked about it's not just meteorologists, but why is a team like this so important to the Army, to the Defense, to the Department of War and operations? Is I think during our earlier conversation you and I had is that, training happens outside. Military installations are affected. So why is the information that you and your team provide and the research you conduct kind of crucial to the Army, Department of War, and other services?
Yeah, so I think a lot of what we do is like you said, a lot of what the Army does is outside. So basically everything the Army does is in some way or another affected by the weather. And a lot of the weather problems that we have today are oftentimes, especially with respect to the Army, who operates at ground level, are not just, the atmosphere itself, but really the interaction of the atmosphere and the specific terrain surface that the Army's operating in. For example, whether they're at the mountains where there's a lot of rocks and snow and other things that are affected by the weather, but aren't necessarily only in that atmospheric space. And that's where I think our team aims to sort of find ourselves, or find the unique and difficult to solve research and development problems, is often where those two things meet.
So let's get into the challenge that some of your latest work and stuff has sought to solve. This work builds upon previous models. Those also focused on projecting the path and severity and potential impacts of dust. Why is that such a critical thing, or in this case, weather event to monitor when it comes to military operations?
So yeah, airborne dust, to me, it's one of those sort of pesky, dynamic aspects of the terrain space that really does require special consideration during the mission planning and operations phase. Um, I think as a, you know, collectively, we have a pretty good idea of where the dusty regions in the world are, and where airborne dust is likely to affect military operations. I think, North Africa or across the Sahara Desert, there's a good opportunity for someone to say, yeah, we probably need to worry about dust if we're going to be over there. What I think we're less good at is predicting exactly where dust is going to be an issue on any given day, and then how bad of a problem it's going to be. Um, there's a lot of reasons for that. Dust emission typically occurs at really small scales, and they're over very specific terrain features, and it's really difficult for existing models and techniques to capture this. Um, the upshot is we're good at understanding global and regional average dust climatologies. We can say pretty confidently there's a good chance of dust in the desert, but we're less good at saying dust is going to be a major problem 2 days from now in Morocco. Um, and being able to predict these, what I'm going to call discrete events, is crucial, because dust does everything from, it makes visibility bad, that can make soldier safety a problem. It can obscure our view from the air or from space. We can no longer see what's going on the ground. And more to the point, it's an abrasive material moving at high speed. It degrades equipment, and in particular, aircraft or anything that really has moving parts, could stop functioning if it's hit by a surprise dust storm and that it's not prepared for. The lifetimes of our equipment go down faster in these environments. So being able to accurately predict dust and plan for all that is kind of critical to how we operate in these places.
In the opening, we mentioned the Indo-Pacific region, a large portion of the world where the U.S. military and its allies must operate efficiently. What role do these types of weather models serve military planners? I know we mentioned, maintenance and ish, but what are some other ways that having accurate dust modeling or being understand the sources of that dust affect military planners or support military planners?
Yeah, that's a good question, and I'm gonna start with just by saying I don't have a military background myself, so I can't speak exactly to the role of these models in any real specific detail. But um, again, dust is part of the dynamic terrain in this region, and I think here, more so than perhaps CENTCOM, dust is a much more transient feature. It's not something that's there all the time or something you have to worry about all the time. It's got a specific season, and because of that, I think being able to predict these discrete events is all the more important. Um, Moreover, the dust sources in this region that really do cause these high impact events um, vary seasonally due to things like snow, vegetation, etc. So the improvements that we're doing to characterize the seasonality of these sources are, I think, critical to getting better dust predictions in the region. And I think that, the people planning and using these tools really need that to gain a holistic picture of the challenges um, that they may see in this region, and then also downstream. These events carry across the Sea of Japan, Korea, and out into the Pacific as well. So they're not just kind of local in the region; they really do affect a lot of things in that part of the world.
So this research focuses on an interesting phenomenon in the Gobi Desert, the overlap of the dust season and winter's end. Can you explain why the presence of snow and frozen soil is such a difficult variable and why previous models struggled to account for it?
Yeah, with respect to dust forecasting, I think it may be less that snow and frozen soil themselves are difficult to predict. I don't want to underplay the challenges with doing that. There are certainly challenges there. I think it's just more often we don't usually think of dust storms as occurring in cold regions. I think the general mindset we have is dust storms occur in deserts, and deserts are hot, so we don't have to worry about things like snow and frozen soil. And a lot of the dust models that are used were really developed with a global picture in mind. And what I mean by that is they were developed to really accurately characterize the biggest contributors to the global dust load, which really is the Sahara Desert, and North Africa and West Asia. So not places that experience a lot of snow. Um, but the Gobi Desert is unique. It sits pretty far north, and the dust storm season uh, typically overlaps with the transition from winter to spring when snow and frozen soil, and more so interannual variability in those, can kind of control the dust emission, and in some instances be a driving force in these storms. So, really, what we're trying to do is better quantify that role and understand how these variables can affect dust emission. And again, our hope is that this work can really, aid the METOC community in better forecasting these pesky discrete events that are oftentimes such a challenge.
Well, I'm gonna get back to kind of the differences in just a second, or some of the differences that this model versus previous ones, specifically how they help. But a major role of this work was also reducing the false alarm, right? I think you and I talked at one point, the boy who cried wolf of forecasts. Could you explain what that means and how a more accurate forecast helps commanders avoid what would be honestly an annoying or ultimately costly scenario?
Yeah, false alarms, are I think they're oftentimes underappreciated, but they're a real problem in the weather forecasting community. Whenever and by we I mean meteorologists, predict a big event and it doesn't happen, there's the immediate direct um, consequences of that. Wasted resources. Maybe we ground operations for the day. We don't go out and train. We missed an opportunity to do something. There's the direct consequences and costs of that missed event. But also, you know, there's a serious, loss in trust that can occur when you miss a big event. Stepping back to my roots, I grew up in the Mid Atlantic. Um, you know, and in the Mid Atlantic, anyone who's grown up there, we grew up, we'd watch the TV and just kind of wait on bated breath when we'd see the weather forecast to see if they were going to cancel school because of snow. We all wanted a snow day. And I think everybody, if you talk to anybody from that region, they will have a story where, they canceled school the night before for a blizzard, and I woke up and it was a bluebird, it was a sunny day, there was no snow at all.
Right.
You know, everybody's got that story. And the reason I want to mention that is, people really remember the missed forecast. I think more so than even the big one that does hit, they remember the time that you missed. Um, so coming back to the military world and the world of dust, you know, these storms are challenging to forecast because they require both an accurate weather forecast, which is hard, um, and an accurate characterization of the soil surface, which is also hard. Um, so, when those two things don't align, and let's say the wind speed doesn't overlap with where the dust source is, you can have a busted forecast, and that degrades trust in the METOC community. That degrades trust from the decision makers, um, which again leads to, as you said, that boy who cried wolf situation. So, really, we're trying to improve that and kind of reduce the number of false alarms.
So as this goes back to the differences of this model versus other ones, how do you go back as these models are laid out and these forecasts are made? What are steps that follow after an event? And I would imagine, that's the validation world. How do you go back and try to, self check yourself or to make the models even smarter, better moving forward?
Really, what we try to do as a team when we're doing some of the dust related research that we've done in the past is we'll go back and use the models, and we will really dive into looking at what caused the forecast to go wrong, or what caused the model to not do well? Was it the weather forecast wasn't very good? Maybe the winds were in the wrong place, or they weren't strong enough, or they were too strong. And we will look at, kind of how we can configure the model to improve upon that if it's necessary. And then we'll look at the dust side of things separately. We'll say, okay, well, do we think we were characterizing the soil surface well? How well were we characterizing where the dust sources were? Is that one of the reasons that things weren't working well? And we'll compare it to satellite data to try and identify, where did the dust emission occur during this event? Does that line up with the model? Was it a transport issue? And really kind of dive into all the different pieces that basically led to the event either happening or not happening.
So that kind of leads me to my next question is the phrase that we hear almost in every parts of our lives now, artificial intelligence. And I think it's been described as, in many ways, in many fields, as a new and somewhat disruptive tool, if I could say disruptive correctly, a little bit more effective there, a new and disruptive tool. How do you see AI working alongside these models, traditional models, and to change what you see in applying this type of weather research?
Yeah, yeah, AI is definitely new, exciting, and I'm not scared. I'm not afraid to admit it here. It's kind of scary, in a lot of ways, especially in sort of the meteorology space, and in particular numerical weather prediction, which is my background. Um, yeah, I'll highlight numerical weather prediction first. I don't think it's much of an exaggeration to say that, our entire modern weather and environmental modeling architecture, that's the physical and dynamic models that we use, the supercomputing systems, the data assimilation systems, everything that brings all this together. I don't think it's an exaggeration to say that this is, a modern wonder of the world. It's kind of incredible to me when I step back and think about it, that this is, something that we actually have that works. Um, and I'm even more impressed when I think of how much the technology has evolved, grown, and matured over, really the last 15 years. That's nothing of short of kind of mind-boggling to me. But these models are really expensive to run. They're very, running a model is very data intensive. It's very computationally expensive. And it's also time. It takes a lot of time to run these models. These AI-based weather models, from what I've seen, are remarkably, they're impressive. They're quite accurate. And then once you actually have the model trained up, they require a fraction of the cost. Yeah, it saves time, it saves energy, it saves money. Um, it's a really, I think the research community is right in moving into a direction where the mindset is changing to think, a lot of our focus is going to be on these AI tools rather than the traditional approach. Um, I think traditional NWP is always going to play a role. Uh, AI models are only as good as the data that we use to train them, and a lot of this data is very heavily reliant on what the traditional models put out. Um, the traditional models also ground us in real life physics. Um, AI models, don't care about physics or dynamics. They just care about minimizing that cost function. Um, and so they don't know about the what's going on in reality. Um, I think there's some larger, almost philosophical questions to tackle too, from a decision making standpoint. Sure, AI is going to help us generate a whole lot of new data. Um, is that new data actually going to help us make a better decision than what we're currently using? And I think these are all questions that need to be answered going forward. But yeah, it's definitely an exciting time to be in this research area.
To get going back to the model, to get the level of accuracy, this new level of accuracy that your team developed for, you developed more precise. Well, I think you described it one time as dust emission maps. Can you explain how these maps were developed and what made them so much more precise than previous versions?
So this was, a little bit of this. A lot of the previous versions are still based off of this idea that we're just looking at characterizing the global sources better. So they're kind of coarse. They're not all that advanced in terms of how they were developed. Um, But I think in developing these dust emission maps, I think this really highlights the interdisciplinary aspects of our team. Um, Basically, we had a bunch of different remote sensing data sets from satellites. Um, we combined that with machine learning techniques to get global maps of what we call landform classes. So we can classify, all the different landforms, and we can do that at a 500-meter pixel size. So it's really fine scale detail um, compared to, say, the resolution of a modern numerical weather prediction model. Um, we then turn these into a dust emission potential using field data that was collected across these, various land surface classes. Um, so a lot of that work was performed by the geomorphology and the remote sensing expertise that we have within our team, and then the meteorologists of our group took that information and actually integrated it into the weather forecast models that are used to make these predictions, and then also to do a lot of the testing and evaluation. Compared to the current maps, we get much finer spatial detail of the dust sources across the globe.
So, going back to the dust question and these maps and stuff, that was a very scientific term, stuff. When we talk about dust, we also about weather events. What are some areas, and I guess Gobi Desert was one of those, that would be other areas where dust would be an oddity, would be a unique problem set that people wouldn't traditionally think of? Because, you mentioned about growing up, in the South, we often hear about the dust being transported from the Sahara Desert into the Gulf area, and, it makes for vibrant sunsets or whatever the case may be, or weather or air quality issues. What are some other areas that people may not be aware that dust is a challenge?
So, and I'm sure that some of these places, if you find someone who lives there, they're going to tell you, "Oh yeah, dust is a challenge," because they've seen it. But I think a lot of one of the places that's actually fairly unique is across the central United States. Um, you don't often think about dust as being a problem across the central United States, with the exception of maybe some historical references to the Dust Bowl.
Oh, yeah.
But agricultural activities and tillage of fields and a lot of things, when aligned right, dust can be kind of a large problem across the central United States. I believe there was a big event. I want to say it was last spring. Uh, Again, similar to the Gobi Desert, shortly after the snow melted out, but before anything started growing, we had a really strong cyclone move across the middle part of the country, and it stirred up a ton of dust across Texas, Southwest Colorado, Oklahoma, which caused issues in Chicago. You know, Places like that are occasionally affected by dust storms. And I don't think we typically think of those places as dust prone. Again, they're not deserts. And a lot of the places where the dust came from aren't always or necessarily thought of as deserts. The Southwest United States, I think we often think of as dusty, but especially as we move up to the Colorado Plateau in Utah, that's another place that has dust that is often affected by things like snow or frozen soil. And that dust goes on to, affect the snowpack in the Colorado Rockies. So, other, interesting things that kind of connect back to the dust, just locally to the continental United States.
Which also, like, you go back to our first part of the conversation, affects, military installations, training opportunities,
Right.
also civilian operations as well. So it all, comes back to that dust impact. So now that you've proven the importance of these ground conditions, what are the next steps? Where do you see additional improvements for this and other models coming from?
I'm going to try to give a real short answer here for once. I think really the role of vegetation and maybe non-vegetated obstacles um, that maybe affect dust emission and really the wind stress at the ground surface could be better characterized. And I think there's a lot of exciting research that can be done in that area, which would improve even more upon kind of our dust emission forecast.
So as you go back and now check, and now this model's running and you're validating it and stuff and such, what are some new applications? I mean, is there a new, what's the next challenge for you, your team, and this model in particular? Is there a next challenge, another region where such a challenge is to be discovered?
So I think, yeah, so this is a good question. I'm going to try to give you the best answer that I can here. So a lot of what our team is doing is maybe not, at least at the moment, focused explicitly on the dust emission and the dust transport problem. A lot of that technology has actually been transitioned into, kind of the operational weather models used by the Air Force. But what we're doing is we're applying a lot of the same techniques that we developed to look to basically generate these dust emission maps that are in the model, and to generate a lot of the research that we did into dust. We're using a lot of those same techniques to tackle other problems right now that seem to be of interest. So, one of the ones that we looked at recently is characterizing thawing mud. Um, that's a big problem in a lot of the regions of the world that have freeze thaw and snow as well. But we're taking a lot of the tools that we developed and trying to find new applications for them.
Well, sir, listen, I appreciate the time today. I appreciate the time we've had, previously as well, to better understand, not just this model, but the impact that the weather effects team has. I still think, the abbreviation for your team is WEXET, WEXET, right? I think you
Yes.
missed an opportunity with weather effects team being wet. I think that would have been a great acronym. It'd have been I'm not sure how we can get that changed if we can go back, but I understand, and you're going to stick to that. But I do appreciate the time. I appreciate the opportunity to discuss this topic, and I'm sure plenty of people will have questions and seek some more information. So for those who do, you can email erdicinfo@usace.army.mil for more information, and we will get those connected to Dr. Letcher and the weather effects team. And you could always go back for additional resources on this topic. You can go to poweroferdicpodcast.org, click on the more resources tab, and you can get some additional resources on their research. And for that, sir, again, thank you. To the audience, I say thanks as well, and we will see you next week.
Great. Thank you for having me.